My name is Abdel Rahman Tawil. I'm a professor of software engineering at Birmingham City University. I'm leading the DIATOMIC BCU team on developing a traffic and air quality digital twin for the DIATOMIC project. We are now at phase 2 of the DIATOMIC project, and our group is focused on core platform technology developments, including accessibility, usability, API frameworks, and security compliance. Our presentation will consist of 2 parts. A high-level overview of the project, which I'm going to go through very quickly. I'm going to whiz through it. And also I'm going to show the architecture quickly. And then we will have a demo of the application. So the Traffic and Air Quality Digital Twin, or we're calling it TAC-DT, is developed by Birmingham City University as part of the DIATOMIC program. At its core, TAC-DT is a platform that ingests real-time data from hundreds of sensors deployed across the city, covering everything from vehicle flow to air quality levels. The digital twin integrates AI and machine learning models, enabling simulation and forecasting of various scenarios, such as changes in traffic flow, vehicle types, or even impact of school holidays on pollution patterns. Ultimately, through real-time monitoring, predictive modeling, and intuitive visual communication, TAC-DT supports the creation of smarter, healthier, and more sustainable urban environment. One of the key outcomes of the digital twin, or TAC-DT, is to build a virtual replica of transport and air quality dynamics in the Birmingham Clean Air Zone. So we will provide a demonstration of TAC-DT towards the end of this presentation. But let me start by introducing the broader program that underpins our work on the DIATOMIC initiative. So DIATOMIC is a 3-year project funded by Innovate UK and the West Midlands Combined Authority. DIATOMIC stands for Digital Innovation Transformative Change. In the first 2 years of the project, and in partnership with Connected Places Catapult and the 3 universities in Birmingham, and in collaboration with Siemens Adventa, we developed a base digital twin platform consisting of composable architecture, integrating IoT connectivity, visualization tools, and a modular containerized framework. The digital twin-based platform has been operational since September 2024, with 3 use cases from the universities have been onboarded onto the Azure platform. DIATOMIC now is in its 3rd year with focus on utilizing the digital twin platform within the Birmingham Knowledge Quarter and Wolverhampton Green Innovation Corridor investment zones to enable cross-sector collaboration, data-driven policy, and economic growth. So this slide introduces the foundational reference architecture behind our digital twin implementation. So the architecture is designed in distinct layers, with each layer building upon the previous one to ensure modularity, scalability, and interoperability. At the base, the city layer represents real-world systems, IoT sensors, air quality monitors, traffic systems, and external platforms like early and AirViro sensors. These provide the core data feeding into the twin. Then the data management layer handles the ingestion, structuring, validation, ensuring clean, reliable data for analysis. Then we have the information modeling layer, standardizes data semantics and formats across systems, which is essential for interoperability. Then we have the AI, machine learning analytic layer, which extracts insights and patterns and enabling smarter data-driven decisions. Above that, the application layer turns insight into action through use case-specific tools. And at the top is the communities and SME layer, which is focused on user interfaces and engagement with stakeholders such as council, businesses, and citizens. This layered design allows us to manage complexity while enabling a wide range of urban applications. We are also experimenting with LLMs, large language models, to support augmented ETLs, for example, using generative AI to create data pipelines for automating data extraction and to perform data transformations. We are also experimenting on using LLMs for automated reporting and dynamic dashboard generation. We'll briefly demonstrate the use of LLMs if time allows. So quickly, the next slide goes on one layer deeper into the platform to explore the core of the system, the digital twin engine. The hexagonal architecture represents a packaged business capability. At the heart of this engine is the domain model, which describes the structure, relationships, and semantics of the digital twin components. And then surrounding that is the core, surrounding the core domain model is a rich set of domain services, enabling capabilities. And then the API and domain service layer acts as the gatekeeper and facilitator between the internal logic of the digital twin engine and the external ecosystem. This architecture style ensures that we can flexibly plug in new data sources, use cases, or AI modules without changing the core logic. The result is, up until what we see up to now, is a robust, scalable, and composable engine that powers the different use cases across the DIATOMIC digital twin platform. All right, so I'm going to stop talking, and Naji, our lead developer, will demonstrate the AI capabilities of the traffic and air quality digital twin, and will also showcase how large language models are integrated within the DIATOMIC platform to generate rapid insights. So Naji, it's over to you.
Thank you. Hi, name is Naji. I'm a research fellow at BCU. I'm presenting to you the DIATOMIC solutions. We have two solutions built on top of the infrastructure. What we have is one of the greatest challenges we've encountered when working with traffic and air quality is how do we model the data from individual sensors to holistic models that can include all sensors. Here we have traffic sensors that counts the number of cars, noted by the red color, number of cars and average speeds, and the greens are the air quality sensors, recording NO2, PM2.5, etc. So we can investigate individual sensors on the platform and run through the historical data. So we can see NO2, O3, PM2.5, etc. So what we develop was an AI canvas that allows us to create AI models to make predictions. So we can choose individual sensors to include in our localized models. If I can show you. So from these models, we can train them. The training takes under a minute, given the number of sensors that you chose to put into your localized models. Here's a simple demonstration where we have just two sensors. So we have one input sensor and one output sensor. So we're predicting the output based on the inputs. And we can get some reasonable accuracy here. Showing the model insights. So now the challenge is to how to deduce the right sensors to get better accuracy with our predictions. So we came to a solution to leverage LLMs to find correlation information. So what we're able to do is we can type in queries with the data set and get generative response. And these LLMs will generate the data that will enable us to visualize the data sets. So here I'm requesting top 10 correlations with RTM, which is a traffic sensor. And we're asking for correlations if that traffic sensor has around 17 buses, right? So we can get the results here, and it will return the summary of results, the key insights. And one of the things we realize is how can we make sure that it conforms and aligned with the original query and the prompts that the users provide. So we have an alignment kind of information as well that tells how does this relate to original question, and to explain how the prompts will provide you the right kind of insights. So additionally, we also include limitations and additional queries, and we can also form a recommendation kind of suggestions of follow-up queries that we can create for the traffic inequality solutions. So this is just an example of, because we have around 200 sensors. So how do we find the right kind of combinations of sensors that affects one another? So we have a correlation model that kind of like investigates individual sensors and find the right combination of sensors that with highest strength of correlation that's attributed to that sensor.
So now if we go over to how can the data used in your base digital twin platform be shared for other solutions on the platform? And someone's also asked, or with the public or government. So now to DIATOMIC.
Yeah, so when the data is ingested, it's structured, it's validated, it's cleaned, and it's prepared, ready to be used. So it's compatible with the platform. And when it's compatible with the platform, any application that's plugged into the platform has access to this data.